Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. Dear students, welcome back. This is second part of our this week's first lecture, and in first part we studied about encoding techniques, criteria of selecting suitable encoding technique, and types of data and signal encoding combinations that were digital data, digital signaling, analog data, digital signaling, digital data, analog signaling, and analog data, analog signaling. Four types. And then we started with different parameters to be keep in mind. And after that, we discussed amplitude, uh, digital data, analog signaling. That included amplitude shift keying, frequency shift keying, and phase shift keying. We completed our discussion about amplitude shift keying. We were discussing frequency shift keying, in which we covered the topic binary frequency shift keying BXK, and we were about to start our topic multi frequency shift keying. Let's start. You can see these slides. Here you can see the equation and main points of multi-frequency shift keying. The main purpose of choosing multi-frequency shift keying was that it is less prone to error, in which more than two frequencies are used. What happened in this case? In this case, each signaling element represent more than one bit. In binary frequency shift keying, each signaling element was representing one bit, and it is representing more than one bit. The transmitted multi-frequency shift keying signal for one signal element time can be defined as it is showing here in black text. S I of t is equal to a cos of 2 pi fi of t. If you focus in simple frequency shift keying, here it was a cos of 2 pi f1 t, a cos of 2 pi f2 of t. Here it is not specifying 1 or 2, it is showing I, and this I ranges from 1 to m, where fi is fc means carrier frequency plus 2i, and for the sake of uh, clearing, basically I is number of signal elements, and it ranges from 1 to m. So we can say that carrier frequency plus number of signal elements minus 1 minus m times fd. And what is this fd? Fd is basically difference frequency. the difference between original carrier frequency and the current frequency being used for a particular symbol or particular signal. So we add this difference to carrier to get our frequency being transmitted for this particular symbol or set of elements. So and where m is, which is maximum number of signal elements that a signal can have, it is basically 2 raised to power l. And what is l? Number of bits per signal elements. As I discussed earlier, for a 2-bit signal element, the number of a maximum number of signal elements will be 4, 2 raised to power 2, 4. That is, they can be 0 0, they can be 0 1, they can be 1 0, they can be 1 1. And for 3-bit, if the number of bits per signal elements is 3, then number of different signal will be 2 raised to power 3, 8. Similarly, number of bits per signal element, if there are 4, then total number of different signal element will be 2 raised to power 4, 16. Here, to match the data rate of input bit stream, each output bit stream, output signals element is held for a period of Ts. Again, to match data rate of input bit stream, each output signal element is held for a period of Ts. Ts, what is Ts? Basically, it is product of number of bits per signal element times t seconds. Because if we can say that if a bit is of 1 nanosecond and length of our signal element is 3, then we have to wait for 3 nanoseconds. So t here is bit period. Thus one signal element which is constant frequency tone encodes L bits. The total bandwidth required is 2 MFD. Total bandwidth here is FD times M. Again a confusion. FD is difference frequency. You know, carrier is the center frequency, and uh, we can say that we have to add uh, difference frequency to original carrier. How many difference frequencies we needed depends upon number of total elements. Hope you got the idea. It can be shown that minimum frequency separation required is 2FD, that is actually equal to 1 over Ts. 1 over time duration of 1 bit means minimum value of uh, difference carrier difference will be 1 over Ts, because if we has lesser difference frequency, then there is a chance of getting interference of each signal with the other one. Therefore, the modulator modulator requires a bandwidth of WD, that is equal to 2 MFD, means number of um, uh, number of we can say that different signal elements time carrier frequency required for each set of signal element. So the whole stuff that I discussed, Ts is equal to LT second, and total bandwidth required is 2 MFD, right? Or modulator required bandwidth of 2 MFD, that is WD. And we know that M is equal to 2 raised to power L, just same thing that is repeated, 2 raised to power L over LT, right? Or simply M over T seconds. So don't get confused. This is basically representation of 2L over LT is same as 2 MFD. So modulator actually required 2 MFD of bandwidth. Hope you got the idea. Now it is time to look at the idea of uh, MFSK in terms of graphical representations. It is showing that look have a MFD. Now it is explained 2 MFD means total bandwidth required is how many levels we do need. We need 1, 2, 3, 4 level, and it is showing formula a cos of 2 pi fd. Here we can 2 MFD. So total number of levels are 4. So we need total 4 frequencies, 4 difference frequencies. Look at it. One is carrier plus FD, the other one is carrier plus 3 FD, and the third one is carrier minus FD and carrier minus 3 FD. Got it? So 2M FD is total bandwidth required for our MFSK. So, so total bandwidth is FC plus 3 FD. Let us say if we keeping our FD equal to 100, then what will happen? As shown above in diagram, MFSK with M is equal to 4 and input stream of 20 bits is encoded 2 bits at a time, with each of the 4 possible 2-bit combinations transmitted as a different frequency. The display in figure shows the frequency transmitted, that is being on y-axis, as a function of time x-axis. Each column represents a time unit ts in which a single 2-bit signal element is transmitted. The shaded rectangle in the column indicate the frequency transmitted during that time unit. I repeat, each column represent a time unit ts, means time slot, in which a single 2-bit signal element is transmitted. The shaded rectangle, like this one, this one, this one, this one, this one, these are showing frequency transmitted during that time. Here you can see on left side that uh, there are frequencies being decided for what level, what frequency will be transmitted. So hope you got the idea of MFSK. Now it's time to discuss about PSK, that is basically phase shift keying. What happens in PSK? The phase of the carrier signal is shifted to represent data. Repeat, the phase of carrier signal is shifted to represent data. Basically, there are two levels in data. So basic level PSK is two level PSK. It is the simplest scheme that is being implemented using phase shift keying. So it uses two phases to represent two binary signals, and it is also known as binary phase shift keying. The resulting transmitted signal for 1 bit time is given as, here you can see that, a cos of 2 pi fct, and for the other one is a cos of 2 pi fct plus pi. This pi is representing 180 degree, because a phase shift 180 degree is equivalent to flipping the sine wave or multiplying it by -1. So the this expression can also be used. This leads to convenient formulation. If you are getting confused with this one, you can use this. If we have a bit stream and we defined dt as discrete function that takes on the value of +1 for 1 bit time, if corresponding bit in the bit stream is 1, and value of -1 of 1 bit time if the corresponding bit in bit stream is 0. Then we can define the transmitted signal as, here we can see, for 0 and for 1. It is better to show you the diagram that I showed in previous section, this one. If it is 0, the phase is going in negative, then positive, then negative, then positive, starting from negative pulse. And if it is 1, the phase is automatically reversed. It is first going to 1, then to negative, then for positive, then negative. Here the start of the signal is towards negative. Here the start of the signal is toward positive. Same is that I said, we define the discrete function that takes on value of +1 for 1 bit time. If corresponding bit in the bit stream is 1, the value of -1 for bit time if the corresponding bit in the bit stream is 0. I repeat, this discrete function takes on the value of +1 for 1 bit time if the corresponding bit in the bit stream is 1, and the value of -1 for 1 bit time if the corresponding bit in the bit stream is 0. So we here see BFSK. One thing that is also being used is differential PSK and 4 level PSK as well. But before going to that, uh, FSK is less prone to error than ASK. Okay, we were phase shifting. So I was discussing about the uh, differential phase shift keying is an alternative to BPSK. What is advantage of it? Actually, it is alternative form of 2 level PSK. In this scheme, a binary 0 is represented by sending a signal burst of the same phase as the previous signal burst sent. So that simply it is copying the phase of previous signals. 0 is copying the phase of previous signal, and a binary 1 is represented by sending a signal burst of opposite phase to the preceding one. This term differential referred to the fact that the phase shift is with reference to previous bit transmitted rather than to some constant reference signal. What is benefit of that? In differential encoding, the information to be transmitted is represented in terms of changes between successive data symbols rather than signal elements themselves. Differential phase shift keying avoids the requirement for an accurate local oscillator phase at receiver that is matched with the transmitter. As long as preceding phase is received correctly, the phase reference is accurate. So I think so that the working of our modulator is somewhat reduced as well as demodulator as well. We can use also multiple level PSK. The basic of them is yes, 4 level PSK. It is more efficient usage of bandwidth, and it can be achieved if each signaling element represent more than one bit. For example, instead of a phase shift of 180 degree as allowed in PSK, common encoding technique known as quadrature phase shift keying uses phase shift separated by multiple of 90 degree, means pi by 2. So QPSK, you can see the scheme. Here it is showing for 1 a cos of 2 pi fct plus pi by 4, a cos of 2 pi fct plus 3 pi by 4 for 01, and for 00 a cos of 2 pi fct minus 3 pi by 4, and for 10 a cos of 2 pi fct minus pi by 4. What is happening? It is showing each signal element represent 2 bits rather than 1. We can see our this one. This is basically a technique where we can use implement QPSK. We can phase shift of pi by 2 here. This is actually carrier oscillator, and here 2 bit is coming at this position, and 2 bits, same 2 bits are coming at this position. This is basically implementation of QPSK. The input is a stream of binary digit with a data rate of r, and this, if data rate of r is, what will be the duration of 1 bit? Exactly, the duration of 1 bit will be 1 over TB, or I can say that TB is the width of each bit. This stream is converted into two separate bit streams of r by 2 bits, r by 2 bits per second each. As you can see, one is going above and one is going down. By taking alternative alternate bits for the two streams, two data streams are referred to as in phase, means I, and Q, means quadrature phase. In the diagram, the upper stream is modulated on carrier frequency by multiplying the bit stream by the carrier. For convenience, the modulator structure we map binary 1 to underscore uh, root square 1 by 2 and binary 0 to minus under root 1 by 2. Thus, a binary 1 is represented by a scaled version of the carrier wave, and a binary 0 is represented by a scaled version of the negative of carrier wave, both at constant amplitude. This same carrier wave is shifted by 90 degree and used for modulation of lower binary stream. The two modulated signal are then added together and transmitted. The transmitted signal can be represented as you can say here. Basically, you have to put 1 by 2 with the same formula. One is one the QPSK will be S of t is equal to here you can see formula A cos of 2 pi FCT. Here you are seeing the formula, but QPSK will be 1 by 2 I of t cos 2 pi of FCT and minus 1 by 2 q of t sine 2 pi of FCT. Little bit change in formula, but its implementation is quite easier. Basically, each of two modulated scheme in BPSK signal at half the data rate of the original bit stream. Thus, combined signal have a symbol rate that is half the input bit rate. Note that from one symbol time to the next, a phase change of as much as 180 degrees possible. One more, we can say that one more variation of QPSK is offset QPSK. Full name offset quadrature phase shift keying, or other name is orthogonal quadrature phase shift keying. The difference is that delay of 1 bit time is introduced in Q stream, resulting in uh, the same equation that I narrated before, but there will be a delay of 1 bit, and that's because OQPSK differs from QPSK only by the delay in Q stream. It is spectral characteristic and bit error performance are the same as QPSK. The main idea that I explained that uh, for QPSK, in one analog signal there are two bits that are represented by four different equations. The next one is here you can see uh, multi-level PSK. The use of multi-level PSK, multi-level can be extended beyond taking bits two at a time. It is possible to transmit bits three at a time using 8 different phase angles. It is quite possible. Further, Each angle can have more than one amplitude. For example, standard 9600 bps modem means bit per second modem uses 12 phase angles, 4 of which have two amplitude values for a total of 16 different signal elements. I repeat, our normal 9600 bps modem uses 12 phase angles and 4 of which have two amplitude values, so total 16 different signal elements. This example point out very well the difference between the data rate in bit per second and the modulation rate, that is baud rate D. Here you can see the D is baud rate. Let us assume that this scheme is being employed with digital input in which each bit is represented by a constant voltage pulse, one level for binary 1 and one level for binary 0. The data rate R is equal to 1 over TB. Bit duration, bit time, whatever you want to say. However, the encoded signal contain L is equal to 4 bits in each signal element using M is equal to 16. Different combinations of amplitude and phase. The modulation rate can be seen to be R by 4 because each change of signal element communicates 4 bits. Thus, line signaling speed is 2400 baud, but the data rate is 9600 bit per second. Now you are watching the difference between baud and bit per second. This is the reason that higher bit rate can be achieved over voice gate lines by employing more complex modulation schemes. So formula is, I repeat, D is equal to R over L. Modulation rate in baud is equal to data rate in bit per second over L, number of bits per signal elements. Now it's time for looking at performance. While looking at performance of various digital to analog modulation scheme, the first parameter of interest is bandwidth of the modulated signal. This depends on a variety of factors, including the definition of bandwidth used and filtering technique used to create the bandpass signal. We will use some straightforward results at shown. The transmitted bandwidth Bt for ASK of the form is equal to 1 plus R times R, where capital R is the bit rate and small r is related to technique by which the signal is filtered to establish a bandwidth for transmission. Typically value of small r is 0 to 1. Thus bandwidth is directly related to the bit rate. The preceding formula is also valid for PSK. and under certain assumptions for FSK as well. But with multi-level PSK, it is somewhat changed. Multi-level PSK, you can see here, it is equal to 1 over R, sorry, 1 plus R over L times R, and L is equal to log 2 of M. And you know what is L? Number of bits encoded per signal element, and M is the number of different signal elements. And again, for multi-level FSK, bandwidth is 1 plus R times M. Here I have to change it, shift it. Here it is better. It's better now. So 1 plus R times M over log 2 of M times R. So we have a good idea of our bandwidth for different encoding techniques. Now we will see, basically we have studied quadrature amplitude modulation, uh, that was quadrature phase shift keying. It is same idea that was used in quadrature phase shift keying, but there is something enhanced. So quadrature amplitude modulation is a popular analog signaling technique that is used in some wireless standard. This modulation technique is a combination of ASK and PSK. As I earlier said, quadrature amplitude modulation can also be considered a logic extension of QPSK. QAM takes advantage of the fact that it is possible to send two different signals simultaneously on the same carrier frequency by using two copies of the carrier frequency, one shifted by 90 degree with respect to the other. For a quadrature amplitude modulation, each carrier is amplitude shift keying modulated. The two independent signals are simultaneously transmitted over the same medium as at the receiver. The two signals are demodulated and results combined to produce the original binary input. As shown, you can see in the figure, you remember I used the same figure for the QPSK as well. It is showing QAM modulation scheme in general terms. The input is a stream of binary digits as were in QPSK, arriving at a rate of R bit per second. This stream is converted into two separate bit streams of R by 2 bit per second each. Again, as per QSP, it was happening by taking alternate bits for two streams. In the diagram, the upper stream is ASK modulated on carrier of frequency FC by multiplying the bit stream of by the carrier. Thus, a binary 0 is represented by absence of the carrier wave, and a binary 1 is represented by the presence of carrier wave at a constant amplitude. The same carrier wave is shifted by 90 degree and used for ASK modulation over the lower binary stream. The two modulated signal are then added together and transmitted. Here, this portion is same as were in QPSK. This portion is same as per QPSK, but here it was simply phase modulating in QPSK. That was phase modulating, but here it is amplitude modulation, means amplitude shift keying. The only difference between QAM and QPSK. If we use uh, two level ASK, that can also be used, then each of the two streams can be in one of the two states, and combined stream can be in one of the four states. This is essentially QPSK. If four level ASK is used, then combined stream can be of in one of the 16. Means the same block can be repeatedly used to combine different streams. System using 64 even 256 states have been implemented. Wow. The greater the number of states, the higher the data rate that is possible with the given bandwidth. Of course, as discussed previously, the greater the number of states, the higher the potential error rate as well, due to noise and attenuation. So far as we have discussed uh, phase shift keying and combination of phase shift keying and uh, amplitude shift keying. In next lecture, we will discuss analog data and analog signal, and we will conclude our topics in next lecture, inshallah, and we'll start next chapter, inshallah. Till then, take care of yourself. Allah Hafiz. And if you have any queries, you can ask on Google Classroom. I will for sure answer your queries. Thank you.